Galvanometer is said to be more sensitive when it produces large deflection for a small current or voltage. Small current or small voltage, because we can convert galvanometer into a voltmeter also. That is coming next. Okay. So galvanometer is more sensitive when it produces large deflection for a small current. That is sensitivity. Then we can tell galvanometer is very sensitive. Oh, it is showing very large deflection for a small current. So that is the sensitivity of the galvanometer. Then next, current sensitivity and voltage sensitivity. Next, what is meant by current sensitivity? When it is a current sensitive, it is denoted by I. I means current, S means sensitivity. Current sensitivity is defined as the ratio of deflection produced to the current flowing. Current sensitivity is phi by I. Phi by I. Deflection produced to, that means deflection per unit current actually. Deflection per unit current. Current sensitivity. Deflection by current. So according to the equation, it becomes equal to NBA by K, because K phi equal to NIBA, K phi equal to NIBA. So phi by I equal to NBA by K. When is it more sensitive? Current sensitive. Depending on this equation, you can tell when is the galvanometer more sensitive. You can increase the value, increase this N, increase the value of B, increase the value of A, and decrease the value of K. Very important. 1 mark question usually asked. How can you increase the current sensitivity? How can you reduce the value of K? How can you reduce the value of K? K is the restoring torque per unit twist. So that depends upon the material used to suspend the coil, or material used to suspend the coil. So usually phosphor bronze or quartz fiber is used to suspend the coil. So because it is having very small value of K. Which one? Quartz or phosphor bronze fiber. So current sensitivity can be increased by increasing the strength of the magnetic field. Strong magnetic field we can use, increasing the number of turns, increasing the area of the coil, and decreasing the value of K. K is the restoring torque per unit twist. For that, what material is used? Phosphor bronze or quartz strip or fiber are used to suspend the coil. And there are some problems in increasing N. When we increase the value of N, number of turns, so many turns are wound on the coil. What happens if number of turns is more? It becomes bulky. That is a problem. Then if we increase the area, that also increases the size of the coil. That is also difficult. One, increasing the area, increasing the size, etc. That is a problem. But the only thing practically possible is increase the value of B and decreasing the value of K. Practically, that is possible. When you tell the factors, you can tell all the factors, but there are certain limitations in increasing the number of turns and increasing the area of the coil. Next, voltage sensitivity. Voltage sensitivity is defined as deflection produced in the galvanometer per unit potential difference. Deflection per unit voltage. Deflection per unit. When a unit voltage is applied, what is the deflection produced? That is the deflection voltage sensitivity. It is defined as the deflection produced in the galvanometer when unit potential difference is applied across its ends. NIBA equal to K phi. From that equation, I equal to K by NBA into phi. When we know V equal to IR, according to Ohm's law, V equal to I into R. So we have written this value I. This is I into R. So K by NBA R into phi. So voltage sensitivity means deflection per voltage. This is voltage, and this is deflection. So deflection per voltage becomes NBA by KR. This is an current, NBA by K. So voltage becomes NBA by KR. NBA by KR. Okay. Voltage sensitivity can be increased by same factors. NBA by KR is the formula, So increasing the magnetic field, increasing the area, and decreasing the restoring torque per unit is, that means decreasing the value of the same factors. But one thing you must be careful. When voltage sensitivity is independent of the number of turns. Independent of the number of turns, because when number of turns increases, resistance also increases in such a way that N by R remain constant. Let us go back to the equation. But this equation is voltage sensitivity. Yes. You see this equation, voltage sensitivity equal to NBA by KR. So when we increase the number of turns increasing means length we are increasing. When we increase the length, what happens? The length of the wire which is winding on that soft iron core, that is increasing. Length of the wire winding over that soft iron core, that we are increasing. Number of turns increase means length is increasing. Wire length is increasing. So when we increase the length, what happens? Resistance also increases. That we know. Resistance is directly proportional to length. So when we increase the number of turns, what is the problem? Resistance also increases. So the N by R becomes a constant. N increases, R increases. Suppose N is doubled, resistance also doubled. So what happens? There is no effect in it. By increasing the number of turns, voltage sensitivity will not increase, but current sensitivity doubles. Okay? That factor is also an important point. By increasing the number of turns, voltage sensitivity may not change, but current sensitivity, if it is double, it will be double. Okay. Next, conversion of galvanometer into an ammeter. Conversion of galvanometer into an ammeter. You see, how will you convert galvanometer into an ammeter? You can actually you can do in lab. Here a galvanometer will be given to you, and some small wire, that means resistance very small. Such a wire is also a wire or resistance will be given to you. Very small resistance wire, which is known as shunt resistance. Shunt resistance. This is shunt resistance. So here, how will you convert galvanometer into an ammeter? What is an ammeter? Ammeter is a device used to measure current through the circuit element. And galvanometer is also measuring current, but very small current. And we can convert that galvanometer into an ammeter to measure large current. How? By connecting a small resistance in parallel to that. So this is galvanometer, and we connect a small resistance. What is the name of that resistance which is connected parallel to it? Shunt resistance. Shunt resistance. So by hearing shunt resistance itself, you should be knowing that a very small resistance which is connected in parallel to the galvanometer. So only to do that one. But while connecting it, we should know to what scale you have to convert that galvanometer. 0 to 3 ampere, 0 to 5 ampere, 0 to 10 ampere. So like that, you should know. To ammeter, which scale it should measure. how much current it should measure. According to that, we connect a resistance in parallel to that. Not any resistance we are not connecting. So first of all, we have to find out to what scale or the making ammeter should measure what current. That first we have to decide, and then according to that we connect a suitable resistance, and to give the that same, for example, suppose this galvanometer we are converting it into measure 0 to 3 ampere current. So by calculations you have to find out which resistance is to be connected. So that is with calculations only we can find out. Suppose if it gives a deflection, n scale divisions are there. I'll show you that. So connection understood? Simple. Connection is simple, but calculation is there. What resistance we should connect, what value of shunt resistance we should connect to the galvanometer to convert into read a particular value of current, 0 to 1 ampere or 0 to 3 ampere. To what scale it should read. That by calculations you have to find out which is the suitable resistance that should be connected parallel to the galvanometer to convert it to read 3 ampere, 5 ampere, like that. So that with the calculations you have to find out that value and then connect it to the circuit in parallel, then that will read that much current. Okay, that is by calculation only we can find out that. Let G be the resistance of the galvanometer and S be the shunt resistance. Ig be the maximum current that can be passed through the galvanometer. Maximum current, Ig, all values are important. Ig means, suppose when we connect this galvanometer, which is converted into an ammeter in a circuit, suppose Ig is the current flowing through the maximum current that is flowing through the galvanometer, and I be the current that is to be read. I will show the figure again. Listen here. This figure you look. I is the current sent. This is the main circuit part. Suppose in one circuit we are connecting, Ohm's law circuit we are connecting some ammeter. So this is the main circuit and this is the total. This together is known as ammeter. Galvanometer and shunt resistance together is known as ammeter. And I is the current, main current that is flowing. And this is having a resistance. Galvanometer is having a resistance. So depending upon the value of the resistance, the current will flow through that. Ig, suppose we are taking Ig is the current flowing through the galvanometer. And this resistance is a very small resistance. So depending upon this resistance, that current, remaining current will flow through that. So I is the main current reaching here. Ig current, depending on the resistance of the galvanometer, Ig current will flow through it, and the remaining current, we know junction rule, according to the junction rule, remaining current is flowing through that. So I minus Ig will flow through the shunt resistance. And when it reaches here, both the current add and I current will flow through the main circuit. I current here. Here Ig, here I minus Ig, both add together, and the sum of the current, that is I, will flow through the main circuit. So here the potential difference across this galvanometer. What is the potential difference across this galvanometer? Ig into its resistance, Ig into G. What is the potential difference across the shunt resistance? What's the current? I minus Ig into what is the resistance? S. I minus Ig into S. That is the potential difference across shunt resistance. And they are connected in parallel. So we can tell potential difference across the galvanometer will be same as potential difference across this shunt resistance. That is Ig into G equal to I minus Ig into S. Then from that you can calculate the value of shunt resistance. S you can calculate. Potential difference across G equal to potential difference across shunt resistance. That is Ig into G equal to I minus Ig into S, and therefore S equal to Ig into G by I minus Ig. Very important formula for doing problems, application questions. So you should know what all values it represents. As what is meant by S? Shunt resistance. What is Ig? Ig is the maximum current flowing through the galvanometer. When I current is sent through the main circuit, Ig current flows through the galvanometer. That means it shows full scale deflection. When Ig current flows through the galvanometer, it shows full scale deflection. That is the maximum current that can be sent through the galvanometer. Okay, remaining current is flowing through the shunt resistance I minus Ig. So I is the current that is to be measured. I is the current, for example, 0 to 3 ampere. We have to measure 3 ampere current using that ammeter. So that is the maximum current that is to be measured with the ammeter. Even we are sending I current through the circuit, and with the Ig itself it is showing a full scale deflection. When I current is sent, that Ig current flows through the galvanometer and it gives full scale deflection. That means it is measuring I current. Ig current flows through the galvanometer and it shows full scale deflection. Full scale deflection means it is measuring I current. I is the current sent through the ammeter. For I current, it shows maximum deflection. So Ig is the maximum current sent through the galvanometer. See, now all the letters you should know, then only you can do problems and all. Ig is the maximum current that can be passed through the galvanometer. I be the maximum current that is to be read, 0 to 1 ampere, 0 to 3 ampere. Maximum current that is to be read is I. The maximum current flowing through the galvanometer is Ig. S is the shunt resistance. G is the galvanometer resistance. Okay. But with the calculations, you can find out the shunt resistance. When you do problems, it will be more clear. Since shunt resistance S is very low and connected in parallel, the effective resistance of the ammeter is very low. We know in a parallel connection, the effective resistance will be less than the least value of the resistance connected. So what happened? I will show the figure again. See the figure, parallel connection. Galvanometer and shunt resistance are connected parallel. So this is a very small resistance. I told you, galvanometer is having high resistance, but this is a very small resistance. So effective resistance, what will be effective resistance? 1 by R. 1 by R. For example, parallel combination, 1 by RT equal to 1 by G plus 1 by S. And as this value is very small, effective resistance will be very small. Parallel combination, effective resistance is less than the least value. Effective resistance will be less than the shunt value resistance. So what happens when it is connected in a circuit? It will not draw current. Very small resistance. Now this ammeter, now it is not galvanometer. Now when we connect a shunt resistance parallel to it, it is a ammeter. Ideal ammeter is having 0 resistance. Ideal ammeter is having 0 resistance. Why? Because it is maximum current it measures. It measures maximum current. Maximum current measurement resistance should be least. Then only maximum current it can measure. So this ammeter is an instrument having a very small resistance. Otherwise, what happens if the ammeter is having resistance? When it is connected in the circuit, what happens? That itself, this resistance of this ammeter itself, that reduces the value of current in the circuit. That cannot measure the actual value of current flowing through the circuit. because this instrument is having very high resistance. So in effect, the main circuit current will be very less. If ammeter is having very high resistance, what is the problem? Current in the circuit will be very small. That means main circuit current is affected by the resistance of this ammeter. It decreases. It should not happen. Main circuit current should not be affected. We are measuring the main circuit current. But so ideally, yes. Others is it. Others is late. Always late. So ammeter is an instrument having very small resistance. Then only it can be connected in series with the circuit. We know ammeter is always connected in series. Voltmeter is always connected in parallel because voltmeter is having high resistance. Ammeter is having less resistance. Even though it is connected in series, it is not at all affecting the current in the circuit. So that ammeter should have very small resistance. The ideal ammeter is considered to have zero resistance. Understood? So what is the resistance of the combination? 1 by G plus 1 by S. 1 by Rp equal to 1 by G plus 1 by S. Next one.
दोन्ही ऍटमीटर कंपॅरिझन
that is what we have seen here. Shunt resistance equal to Ig into G. What is Ig? Ig is the maximum current passing through the galvanometer. What is G? Galvanometer resistance. What is I? Maximum current, that is red in the ammeter. That means circuit. Maximum current, that is to be red. Then Ig, maximum current flowing through the galvanometer. And here, since shunt resistance S is very low and connected in parallel, the effective resistance of ammeter is very low. So the ammeter will not affect the current passing through the circuit when it is connected in series with the circuit. Okay. Next is conversion of galvanometer into a voltmeter. So conversion of galvanometer into a voltmeter. A voltmeter, everybody knows that. What is a voltmeter? It is a device used to measure potential difference between 2 points in the circuit. In order to convert galvanometer into a voltmeter, what is done? A large resistance is connected series with the galvanometer. So this is a galvanometer. We are converting that into a voltmeter. So what is to be done? A suitable resistance, very high resistance actually. Ammeter, very small resistance connected parallel. But voltmeter, a very high resistance is connected series with the galvanometer because it is measuring potential difference. So maximum voltage should develop across this combination. Then, so here galvanometer G, resistance is also is G. We take galvanometer resistance as G. And this is the high resistance that is connected in series with the galvanometer. So when Ig current flows through it, it gives maximum scale deflection. Scale deflection means what? Here you can see the scale, ammeter, you can see the readings, 1 division, 2 division, 3 division, like that divisions are there. Full scale deflection. And when Ig current sent through this galvanometer, it shows full scale deflection. Full scale understood? 0 is the beginning. Suppose 10 divisions are there on it. Full scale. So Ig current flows it gives maximum deflection. That is the maximum deflection, the Ig. And Ig be the maximum current flows through the galvanometer. That is the meaning. When Ig current flows, it gives full scale deflection. That is the maximum current flowing through the galvanometer. Then Ig be the maximum current flowing through the galvanometer of resistance capital G. Let R be the high resistance connected in series with the circuit, with the galvanometer. Then what from the figure we can see potential difference. This combination together, see why dotted lines are drawn here? Dotted line, did you understand? Because this is single system now. This is a single system now. They are not separate. We have connected the resistance in series with the galvanometer. Together, this is converted. Both of them together is making it a voltmeter. So that's why this don't consider them as separate. This is a single system now. It is converted into a voltmeter now. So it measures the voltage across its ends. It measures the voltage. So suppose we is the voltage that is to be measured 0 to 3 volt. We have to measure 0 to 3 volt, like that, 0 to 5 volt. So we are converting that into a voltmeter to measure V volt, 3 volt, 4 volt, like that. We are telling we want to measure V volt with that voltmeter. And V equal to potential difference. V is equal to I according to Ohm's law. According to Ohm's law, I into total resistance. What is I here? Ig. Ig into what is the total resistance here? G. Series combination, you know. So it will be sum of the resistance. G plus R. G plus R will be the total resistance of this combination. So potential difference will be Ig. Ig with Ig current itself, it is showing full scale deflection. So Ig into G plus R. V equal to IR. Ohm's law. Ig into G plus R. Therefore, G plus R equal to V by Ig. And what we have to find out? We have to find out the resistance. What resistance we should connect to the galvanometer to read V volt. To read V volt, what resistance we should connect? That is given by this formula. V is the voltage that is to be measured, 0 to 3 volt. We want to measure with that voltmeter. Different ranges of voltmeters are available. 0 to 100 volt, 0 to 30 volt, 0 to 5 volt, 0 to 1 volt, like that. Like that, different voltages measuring instruments are there. Voltmeters of different range. 0 to 3 volt, 0 to 5 volt, 0 to 30 volt, like that. Different ranges are available. To what volt we have to measure. According to that, we have to connect the series resistor. And that for that, which resistance we should connect. For that, we should know this equation. V by Ig minus G. V is voltage that is to be measured or that is to be read in that voltmeter. Ig, maximum current flowing through the galvanometer. Capital G is the resistance of the galvanometer. So that formula, two formulas we have studied. We have to convert into galvanometer, not to convert galvanometer into an ammeter. What is the formula? We should connect a shunt resistance S equal to Ig into G by what is it? I minus Ig. Ig into G by I minus Ig. And for converting into a voltmeter, R is equal to V by Ig minus. So remember this formula. Okay, next. I think this portion is our theory part of this chapter, magnetic effect of electric current or moving charges and magnetism. And magnetism is left, that is next chapter. Okay. So this chapter theory part is over, we have to do problems. Let's see. So all of you, I send some formulas to you. For if you by heart the formula, then only we can do problems. And problems, we will be doing some problems, and along with that, you have to do extra problems from reference books or question banks, like that. We will be giving a practice to do the problem, and you have to do extra work on it to get good mark. So let us see the problems now. Okay, this one. Or 5 minutes more is there. All the formulas you have to study. Then only we can do problem. This is 7. Okay, no problem. A long straight wire AB carries a current of 4 ampere. A proton P travels at 4 into 10 raised to 6 meter per second parallel to the wire, 0.2 meter from it and in a direction opposite to the current as shown in figure. Calculate the force which the magnetic field of current exerts on the proton. Also specify the direction of the force. You see, first you have to understand the question. Long straight wire. So you can draw a long straight wire. Long straight wire AB carries a current of 4 ampere. So you can mark 4 ampere current on it. And a proton P travels at 4 into 10 raised to 6 meter per second. So you can mark a proton here and its velocity is marked 4 into 10 raised to 6 meter per second parallel to the wire. It is moving parallel to the wire. At what distance? 0.2 meter from it. So this distance between them is 0.2 meter and it is moving parallel, but one more thing is there from it and in a direction opposite to the current as shown in figure. So the proton is moving with a velocity 4 into 10 raised to 6 meter per second in a direction opposite to the direction of current. Current direction is marked upwards. So opposite to its motion, current direction, the particle is, proton is moving. Okay, that is, so we have expressed all in a figure. Then what's the question? Calculate the force with which the which the magnetic field of current exerts. So we know straight conductor carrying current, around that there is a magnetic field, and when a charge moves in that magnetic field, it experiences a force. Force equal to BQ sin theta. And what's the magnetic field around this wire? Straight wire. That is why I asked you to study the formula. Magnetic field around a straight wire. Misura by 4 pi 2I by R, or you can write Misura I by 2 pi R. Straight conductor, Ampere circuital theorem, we have derived it. All of you study the derivations, study the formulas. Okay, at a distance R from the straight conductor carrying current, the magnetic field is Misura I by 2 pi R. Formulas study very well. For Misura value, 4 pi into 10 raised to minus 7. Misura value. And into I is, what is current? Oh, one thing left. What is the current? 4 ampere. I don't know. 4 ampere. 4 ampere by 2 pi into R, distance R. It is given in meter. So no need to convert. So you just write point here. Then by calculations, you are getting the answer B equal to 4 into 10 raised to minus 6 Tesla. Unit of magnetic field induction is Tesla. Okay. Then force also we have to calculate. We found the magnetic field induction around it, and then we have to find out force. Force acting on a charge. What is the formula? BQ sin theta. Force acting on a conductor. What is the formula? BIL sin theta. What is the torque acting on a coil? NIBA cos theta or NIBA sin alpha. So all formulas study very well. Then a problem you can do. This field acts on proton. Normally, field you have to represent how to represent the field around it. Which rule? Which rule we use? Right hand thumb rule. Right hand thumb rule. According to right hand thumb rule, what is the direction of force field at this point P? I will ask that question. Okay. I will ask to